Let's take a look at some of series solutions of linear differential equations. First of all, recall the definition of ordinary point and the definition of singular point. An ordinary point is a point where the coefficients px and qx are both analytic. What's the meaning of that? It means that they have power series representation, especially if you have polynomials. Any point that lands on the denominator of px, qx are called singular points. We have regular singular point and we have irregular singular points. For a regular singular point, you need to multiply px by x minus x sub 0 and qx by x minus x sub 0 to the second power. If they become analytic at x sub 0, then you have a regular singular point. For example, let's take a look at this differential equation. 2x squared and the second derivative of y plus 3xy prime minus x squared plus 1y equal to 0. First, we need to check to see if we have an ordinary point or singular point. We're going to divide everything by 2x squared. It becomes the second derivative of y plus 3 halves divided by 2, or 3 divided by 2xy prime plus, if you simplify this, x squared plus 1 divided by 2x squared, it becomes negative a half minus a half x squared divided by x squared times y equal to 0. But take a look at these two. Here, if you multiply 3 divided by 2x by x, it is 3 halves, which is just a constant. When you multiply this guy, which is your qx, negative a half minus a half x squared divided by x squared by x squared, it simplifies to this polynomial. Basically, you have a quadratic term, which is basically, again, analytic. So at x sub 0, both of these are analytic. It means that they have power series representation. So x sub 0 equal to 0 is a regular singular point for you. Recall that if you have ordinary point, the power series format is like this. And if you have a regular singular point, then you're going to apply Frobenius Theorem. It means that you have the power series of this format. Very good. So since you have a regular singular point, you're going to apply Frobenius Theorem. You're going to start by taking y equals to the summation Cn x to the power n plus r, take the derivative, second derivative, and substitute in the original differential equation. You get 2x squared times this power series, which is n plus r minus 1, cn x to the power n plus r minus 2, but note that we have x squared here, so 2 and negative 2, it gets cancelled out. The same for the rest of these power series. Now let's try to combine this together, right? The very first power series starts at 0, and the exponent of x is n plus r. You don't have any issue here. Take a look at the second power series. Starts at 0 with exponent n plus r. The third power series, however, starts at 0, but the exponent is n, the power is n plus r plus 2. And the last guy is starting at 0, and the power is n plus r. So the problematic part is this guy here. What are we going to do? We're going to shift this series a little bit. So we're going to try to get rid of the very first two terms by shifting the series. N starts at 2. So as you can see, we're going to shift n 2 units. C sub n minus 2, x raised to n plus r plus 2 minus 2, which becomes n plus r. The common range of summation is n more than or equals to 2. So we're going to deal with the 0th term and the first term separately. What are you going to do? You're going to plug in 0, and you end up with 2 times 0 plus r, 0 plus r minus 1, c sub 0, x to the power 0 plus r. The same for this term. We don't have any issue here, so we're going to leave this as it is. But the last term, again, c sub 0, x to the power 0 plus r. And the same for n equals to 1. So for the 0th term, you end up having 2r times r minus 1 plus 3r minus 1 c sub 0, which can be simplified as 2 times r squared plus a half r minus a half c sub 0 equal to 0. When n is equal to 1, it means that we are working with the first term. So I get 2r plus 1 times r plus 3 times r plus 1 minus 1 c sub 1, which can be written as 2r squared plus 5r plus 2c1 equal to 0. Very good. So if you set the second one equal to 0, you get 2r squared plus 5r plus 2, which is the coefficient of c1. c1 must be equal to 0. And note that from that, you get r equals to a half and r equals to negative. Perfect. The coefficient of x to power n plus r is 2 times n plus r minus 1 cn plus 3 times n plus r times c sub n minus c sub n minus 2 minus cn equal to 0. Very good. So by applying the recursion, cn becomes cn minus 2 divided by 2 times n plus r to the second power plus n plus r minus 1. And note that n is more than equals to 2. Now what? Since r is equal to a half, we can write an in place of cn and substitute r equals to a half. So an becomes, we are just basically going back and forth here. An becomes an minus 2 times 2 times n squared plus 3n by substituting a half here. And basically, you can see that this formula gives us the coefficient in the first Frobenius solution, and we can see that an is equal to 0 if n is odd. And n is equal to 2, 4, 6, you get a sub 2, a sub 0 divided by 14, a sub 4 equals to 8, 2 divided by 44, or a sub 0 divided by 6, 16, and so on. So this is your first power series solution. Now for the second power series solution, you're going to use r equals to negative 1. You can use, for example, bn in place of cn. And then bn is equal to bn minus 2 divided by 2, b squared minus 3n. bn is equal to 0 for odd n values. And when n is equal to 2, 4, 6, and so on, you get b2 equals to b sub 0 divided by 2, b4 equals to b2 divided by 20, and so on. So this is your second power series solution. Take a look at the summary. So what we did, we first determined if you have a regular singular point or you have ordinary point. So you know which method to apply for Frobenius theorem. Then we try to shift this series a little bit so we can make a decision about the recursion here. And then, as you can see, based on the values for r, we can write the power series solutions in 2 different ways.